Hi there. This is a video about all of your derivative rules and a lot of the notation that's involved, okay? So the first thing I want to talk about is the notation. And the first symbol that we have is the symbol d dx. So d over dx. And this is a verb, okay? And that means that you are taking the derivative. So you are taking the derivative, okay? And that if I write dy dx or y prime or f prime of x, these are nouns, and these are your derivatives, okay? And so that's important that we know that, all right? That we can distinguish between what this is, because I'm going to use this notation a lot, ddx, to show us what we're doing when we're doing a derivative. Okay, now let's think about something, okay? What is a derivative? A derivative is a function that generates the slope of a tangent line, so slope of a tangent line at any x value. All right, that's what a derivative does, okay? So the first thing that we want to do is be able to calculate all of our derivatives and be really, really good at that. So let's look at our first rule. And the first one is our constant rule, okay? And constant rule, we want to use the letter C. So C is a constant, and I like to call it as C is a number, okay? And so if I were to take the derivative with respect to x of some number, just any number, remember that we're going to get 0 out of that. And think about why we get that. The reason is because if you have, let's say, the line, y equals x, or y equals, say, 2, all right, the slope of that line at any of those values is 0, and that's how we get that. Okay, the next one is the power rule. And the power rule means that I'm going to take ddx of some polynomial, so like x to the nth power. And what I'm going to do, remember, is we drop down the n, multiply it by x, and raise it to the n minus 1 power, all right? And that's something that we're typically pretty used to, okay? Let's look at the next one. And that's the constant multiple rule. And so if you were to take a derivative with respect to x, and you have some constant that's a multiplier of some function, okay, then what I would do is that I would keep my constant out front and then continue to just multiply by the derivative of that function, okay? My next rule is the sum and difference rule. So if I'm taking the derivative, ddx, of, let's say, the sum of two functions, so f of x plus g of x, then as a result, I'm just going to take the sum or difference of their derivative. So it'd be f prime of x, and we would be adding or subtracting g prime of x, okay? All right, so the next one we have is the square root rule. So if I'm taking the derivative with respect to x of, say, the square root of x, then I get 1 over 2 times the square root of x. Now, you can always do the power rule on this and turn this into, say, the derivative with respect to x of, say, x to the 1/2 power. But then after simplifying it, you get this, all right? If you have a rational, anything other than 1/2, I would recommend using the power rule to do that. Okay, the next one is e to the x rule. Now, this is probably one of your easiest derivatives, but if I take the derivative with respect to x of e to the x, that's simply just going to give me the same thing, e to the x. Okay, the next one's the product rule. And in the product rule, u and v are functions. Okay, so we have to treat them like functions. And so if I were to take the derivative with respect to x of the product of two functions, u times v, then that would give you u times v prime plus v times u prime. Okay, now I could do this in function notation as well. And I could say f of x times g of x. And that's simply just going to give me f of x times g prime of x plus g of x times f prime of x. All right. All right, so with the quotient rule, let's say that we're doing the division of two functions, and I'm taking the derivative with those. Now, I'm just going to use u and v on this. So let's say I take u divided by v. So now this is going to give me v times u prime minus u times v prime all over v squared. And remember, I use that acronym, low d high minus high d low over low low. Okay, and that helps remind me what goes where when I use the quotient rule. Okay, the next one is your trig rules. And so if I were to take the derivative with respect to x of sine x, that's just going to give me cosine of x. Okay? Now, if I take the derivative of cosine, that's going to give me negative sine of x. Okay? If I do the derivative with respect to x of tangent of x, this is going to give me secant squared x. The derivative of cotangent is going to give me negative cosecant squared of x. If I take the derivative with respect to x of secant x, that's going to give me secant x times tangent x. Let me write that down here. Secant of x times tangent of x. And if I take the derivative of cosecant, that's going to give me negative cosecant of x times cotangent of x. Now you're probably wondering how a good way to remember these. Now when I do these, the only things that I remember is sine, tangent, and secant, okay? And so when I do the derivative of sine, that one's pretty easy. It's the opposite. It's cosine. The derivative of tangent is secant squared x. The derivative of secant involves secant x times tangent x. Now, when I'm doing this, when I'm doing the derivatives of the cofunctions, and the cofunctions are cosine, cotangent, cosecant, all right, it's the opposite of what I get for my derivatives of my regular trig functions, and they're all negative. So the opposite of cosine is sine. The opposite of secant squared is cosecant squared. The opposite of secant times tangent is cosecant times cotangent, and they're all negative. So that's how I remember those. All right, one of the most important functions that we can take the derivative of in rule is the chain rule, okay? And so the chain rule states, and let's write this, that u is a function. Okay, so when I do this, we have to know that u is a function, and that's the notation that I'm using. All right, so if I do this, if I say d dx of some composite function, and by a composite function, I mean f of g of x, okay? And what that is I have an inside function and an outside function, okay? And the chain rule is really powerful because it allows me to take derivatives of very, very complex functions, okay? So let's do this. The derivative of this is going to be the derivative of my outside function, f prime, of my inside function, g of x, and then I'm going to multiply that by the derivative of my inside function, g prime of x, okay? And that's the idea, all right? let's go down and let's start doing the rules, the same rules that we would use involving the chain rule. So using the power rule with the chain rule means I'm going to do this. I'm going to take the derivative with respect to x of some function raised to the nth power, okay? And what I want you to notice here is that the x does not match up with the u, okay? When these are different variables, just thinking about how I'm writing these rules, when x and u are different, then you have to use the chain rule, all right? And so what you have is you have this. Same rule. Bring your n down, bring your exponent down, keep your inside function, decrease your exponent by 1, but then you have to multiply by the derivative of the inside function multiplied by u prime every single time, okay? Let's take a look at the next one. So in taking the derivative involving a square root with an inside function, I'm taking the derivative with respect to x of the square root of some function u, okay? And I'm going to use the same rule that I had, except for I need to multiply by the derivative of my inside function. So I'm going to do 1 over 2 times the square root of u, multiply that by u prime, okay? And when I'm doing that, all I really have to do is really just do u prime over 2 times the square root of u, all right? And that's the idea. That's the rule. If I'm applying this to the exponential rule using e to the x, but I'm going to do the derivative with respect of some function e raised to some function u, then I'm going to do the same rule, e to the u power, and then multiply that by the derivative of my inside function, which is u prime, okay? Okay, now doing my derivative of trig rules using the chain rule means that I'm going to do the same thing, but I have to multiply by the derivative of my inside function. So the derivative with respect to x of sine of u is simply just going to be cosine of u times u prime. The derivative of tangent is going to be secant squared u times u prime. The derivative of secant of u is going to be secant of u times tangent of u times u prime, okay? Now looking at the other ones, all right, my cofunctions, remember they're going to be the opposite of what we had, so they're negative, and then the cofunction of that other derivative. So cosecant, the derivative of cosecant of u is going to be negative sine u times u prime. The derivative of cotangent is going to be negative cosecant squared of u times u prime. The derivative of cosecant of u is going to be negative cosecant of u times cotangent of u, and you guessed it, multiplied by the derivative of my inside function, multiplied by u prime. And those are my trig rules. Okay? Now the derivative of my natural log rule means that I'm going to do d dx of the natural log of x. Okay, so now in this example, okay, x and x match. I don't have to use the chain rule here. And all that's going to give me is 1 over x. Now if I do d dx of the natural log of some function u, then I'm going to take my normal derivative, 1 over u, and multiply by the derivative of my inside function. Now 1 over u times u prime is simply just going to give me u prime over u. Now if I do a derivative of just a standard log function, let's do this. d dx of log base b of x. Now remember that b is a number, okay? And so as a result, my derivative of this is going to be 1 over x times the natural log of b, okay? Now if I do d dx of, say, log base b of some function u, all right, then my derivative is going to be 1 over u times the natural log of b, and then we're going to multiply that by u prime. And so we can simplify that and write that as u prime over u times the natural log of b, okay? Okay, and let's say I wanted to do this with just a normal exponential function, not a natural exponential function, e to the x. But let's say I do it this. Let's say d dx of some number b raised to the x power. Remember, b is a constant, b is a number. Okay, and so my derivative then is going to be b to the x times the natural log of b. All right, and then if we apply the chain rule on this, I'm going to get b to the u. U is a function, and so I've got b to the u times the natural log of b, and then multiply it by the derivative of my inside function. Okay, one of the other reasons why the chain rule is so important is it allows us to take derivatives of equations, okay? And this is where we use implicit differentiation, okay? Before, on all of those other ones, we were doing derivatives of functions, okay? Now, not every equation is going to be a function, so it's important that we have the ability to take the derivative of a function itself. So, I want to take the derivative. The standard equation that works best in this scenario is the equation of a circle, and that's going to be x squared plus y squared is equal to 1, okay? Now, if I take the derivative of this whole thing, okay, the derivative with respect to x, I want to take the derivative with respect of each term. So I'm going to do d dx of x squared plus d dx of y squared, and that's going to be equal to d dx of 1. Okay, now, when I look at this, d dx of x squared, taking the derivative with respect to x of x squared, I'm just going to use the power rule. So bring the 2 down, keep my x, 2 minus 1 is 1, so my derivative of that is just 2x. Now, over here on this part, okay, x and y don't match, all right? So I have to use the chain rule here. And so if I'm going to take my normal derivative, so I'm going to get 2y, and then I'm going to multiply by the derivative of my inside function, which in this case is dy dx, okay? This is the same thing as me multiplying by u prime, okay? So my inside function was y, and so I'm going to put dy dx there, and then over here, my derivative of 1 is simply just 0. Okay, so now what I want to do is I want to solve this equation for dy dx. So I'm going to first subtract 2x from both sides, and I'm going to get that 2y times dy dx is equal to negative 2x. I'm going to divide everything by 2y, divide by 2y, and what I end up getting is that I get dy dx is equal to, my 2's are going to divide out here, and so I have negative x over y, and that's my answer. Okay, so on something like this, using implicit differentiation, this is the idea. Now, sometimes a lot of problems, the algebra will be much more involved, but on something like this, you know, this is as easy as I can make it to show you how to use implicit differentiation. Okay, on inverse trig, now this is the dreaded inverse trig. And these are a little bit trickier to manage, but they're not too terrible. So I'm going to go through them the same way as I would the regular trig functions, and talk about sine, tangent, and secant first. The derivative of sine inverse is going to be 1 over the square root of 1 minus x squared. Okay, the derivative of tangent inverse is simply going to be 1 over 1 plus x squared. The derivative of secant inverse is 1 over absolute value of x times the square root of x squared minus 1. Okay. Now, all the other derivatives over here are going to be the exact same thing, except they're just going to be negative. All right. So the derivative of cosine inverse is going to be negative 1 over the square root of 1 minus x squared. The derivative of cotangent inverse is going to be negative 1 over 1 plus x squared. The derivative of cosecant inverse is negative 1 over the absolute value of x times the square root of x squared minus 1. Okay? Now let's talk about using the chain rule with each of these. Now on each of these, they're going to be the exact same thing, except for I need to multiply by the derivative of my inside function, which is just going to be u. So in this case, it's going to be u prime over the square root of 1 minus u squared. Tangent, inverse tangent, is going to be u prime over 1 plus u squared. Secant inverse is going to be u prime over the absolute value of u times the square root of u squared minus 1, okay? Now going back to my cofunctions, okay, same thing, they're just going to be negative. So I've got negative u prime over the square root of 1 minus u squared. When I do cotangent inverse, I'm going to have negative u prime over 1 plus u squared. When I do inverse of cosecant, negative u prime over the absolute value of u times the square root of u squared minus 1. Okay, so those are all my inverse trig derivatives. Yuck. All right, so if we're talking about the derivatives of inverse functions, let's do this. Let's draw out a function. Let's label my x-axis, my y-axis, and then what I know about my generic functions is that I have a function like this, okay? And we're going to call this f of x, okay? And what I know is that when I take the derivative of f of x, or I'm sorry, the inverse of f of x, I reflect that over the line y equals x, okay? And so I end up getting this function here, all right? And we're going to call this f inverse of x, okay? Now, what I know about this is that I have a point on my function, and I'm going to call this the point a, b, okay? Now, if I have my corresponding point on my inverse, and this isn't necessarily drawn to scale, but what I have is I have the point BA. Remember, all I'm doing for an inverse function is I'm just switching x and y, okay? That's the idea. All right, now if I find the derivative of, if I'm finding f prime of A, all right, the slope of the tangent line at A, then really what I'm doing is that's the slope of the tangent line, right? Okay, and when I do this, I get, I have a change in x and a change in y, okay? So when I do this, f prime of A is the ratio of those two. It's the change in y over the change in x. Now over here on my inverse, what I'm doing is I'm taking the derivative of my inverse function. So f inverse, and I'm going to raise that to the prime, make that prime of b, okay? And I'm going to do the same thing. I want to find the slope of the tangent line here. Now what I realize is that I have the same triangle here as I do here, except for it's flipped. But the thing of it is that this same distance here, my change in x, is my vertical length here. So this is the change in x, and then this here is the change in y. So change in y. So when I'm doing the ratio there, all right, I'm just doing the change in x divided by the change in y. All right, so as a result, all right, these two things here are simply just reciprocals, okay? All right, so to put this into context, just to give you an example, let's say that I know that f of 3 is equal to 2, okay? And let's say that I know that f prime of 3 is equal to 3/4, okay? Then if I wanted to find f inverse, I know that I have the point 2, 3. Okay, all I'm doing is switching my x and y value. So if I'm finding the derivative of my inverse, I'm going to find it at the point 2, and all I'm going to do is take the reciprocal, which gives me 4/3. Okay, that's the idea. A little bit weird, a little bit strange, but that's derivative of inverse functions. This video, guys, remember, this is a general overview. All I'm doing is simply writing out all of the rules that are involved with doing derivatives. Your job is that you have to put all this information together and use all of these rules in order to do all of your derivatives. And you got to know them really well. And this is what we learned pretty much in the first, I'd say, 12 weeks of Calc 1. Okay, if you're taking Calc AB, this is what you do. By the time November rolls around, this is all the things that you need to know, okay? So hopefully you got something out of this video, and we'll talk to you guys soon. Thanks a lot. Bye.